called oscillation, is called frequency. This is clear? Okay. Next, what is period? Look here. Period is defined as the time taken by the object to perform one oscillation. Okay, what does that mean? For example, look here. For example, can you look here? Look here. So this is what? It is a sinusoidal signal. For example, how voltage varies with the time. Okay. So there are how many sine pulses? How many sine waves are there? 3 sine waves are there. Okay. This is the first one. This is the first pulse. This is the second pulse. This is the second pulse. And this is the third pulse. Correct? If this duration happens to be, say, 6 seconds. Okay. What is this? This duration happens to be 6 seconds. Okay. Now look here. Suppose you take 6 divided by number of pulse. Number of pulses 3. Correct? No. How many pulses are there? There are 3. 1, 2, and 3. So 6 divided by 3 will give us what? 6 divided by 3 will give us 2. So what is 2? 2 seconds is what? It is the time period of one oscillation. Can you see in this figure here? So what is time period? I'm showing it by the shaded region here. Okay. So what is this? This duration of one pulse, duration of one sine wave is called as time period. Okay. Clear? No. It has been shown by a green dot. Okay. Once again, I'll repeat. How many pulse? What is the duration of this pulse? 6 seconds. And how many pulses are there within 6 seconds? 3. Therefore, 6 divided by 3 will give me 2. What is 2? 2 is nothing but this time period, which I have shown it by blue color. Okay, clear? This is done. Next is, what is equilibrium position? I already told. Next, what is the relationship that exists between frequency and time period? Look here. I think I'll erase all these steps. What is the relationship that connects frequency and time period? Everyone knows frequency F will be equal to, frequency F is equal to 1 divided by T. 1 divided by T. Correct? No? So what is frequency defined as? Frequency of oscillation is the reciprocal of time period. Okay. Next is angular frequency. Angular frequency. For this, let us look at the following video. Okay. Look here. Let me move up. Can you see this following video here? Just look here. A body connected to a spring is oscillating, and behind that there is a paper which rolls.
Helps you rewrite full sentences to improve clarity.
Okay, so look here. In this example, what do you see is there is a body which is connected to a spring. It vibrates up and down. Okay, behind that there will be a sheet. So when the sheet rolls, and if you look at the locus of the point, okay, it will trace a sine wave on the sheet. Okay, just look here. It's very nice. 1 minute video presentation. Okay, the body is connected to a spring, and there is a paper which will roll after a minute. See, the body is connected to a spring and is now set into vibration. Now the paper is set to roll. Okay, so is the video nice? Yes. I think I'll stop this here. Pause. Pause. Okay, pa. Now let us come back to this concept. Okay, where are we here? Yeah. So what is angular frequency? Can you see from the example that? Can you see from the example, the video that I've shown just now? So any periodic signal. So look here, any to and fro motion. Any to and fro motion of the object can be described by a sinusoidal signal. Okay, what does that mean? Look here. Okay, what do I mean by an angular frequency? Look here. Here in the left side, can you see on the left side the body is set into vibration, so it moves up and down. Correct? It moves up and down. Correct? This motion you can also describe as though a particle is moving along a circle. Okay, therefore linear frequency is connected with angular frequency. Okay, clear? No? So how this body vibrates up and down can be connected with a motion of an object along a circle. So therefore all sinusoidal signals, all periodic motions, or rather all simple harmonic motion, can be completely described by a sinusoidal wave. That's what that video demonstrates. Likewise, if an object is performing up and down motion linearly, it can be completely described by an object that is moving along a circle. Okay, therefore somewhere there is a connection between linear frequency f and angular frequency omega. And what is that connection given by? Can you see in my notes? Omega is equal to 2 pi times nu. Can you see here? What is the relationship that connects angular frequency and linear frequency? Omega is equal to 2 pi times nu. How does this follow? Simple. What is that? All linear displacement, or if a body is vibrating up and down, that can be completely described by an object that is moving along a circle. Okay, I already showed. Okay, if an object is moving and if a paper rolls, then it traces a sinusoidal signal. So therefore linear frequency is connected with angular frequency omega. This is clear. Okay, so angular frequency connection is clear. Time period I already defined. What is time period? It is the time taken by the object to perform one complete oscillation is called time period. Okay, can you see here, for example, in my graph here? So if the particle makes one up and down motion, that time that it takes to make one oscillation is called time period. This is done. Next, equilibrium position is done. Relationship between frequency and time period is done. Okay, F is equal to 1 by T, I have already written. Then what is restoring force? Restoring force, I think now I will look at the restoring force. Okay, look here. I'll erase all this, undo. Now look here, pa. So if I pull the object downwards and leave, if I remove my hand here, so will this object have a tendency to move upwards? The object will have a tendency to move upwards because there is a force exerted by this spring on this body. So if I pull the object downwards, force will act in the upward direction. Okay, the force exerted by the spring on this object M, I call this as what? Restoring force. Okay, so what is restoring force given by? Restoring force is given by, see, look here, restoring force is defined as the force exerted by the vibrating system on the body after I withdraw the force. This is clear? No? If I pull this object and leave, it moves up and down. Why does it move up and down? It's because of the restoring force exerted by the spring on the body. The same thing holds good even for a body which is connected to a simple pendulum. So from here, if I leave it, if I take this object, displace it, and if I leave it, what happens? It moves up and down along an angle. So therefore this is done. It's because of restoring force acting on the body. Done. This is done. Next is definition of the simple harmonic motion. Okay, so first let me read out what do I mean by a simple harmonic motion. Look here in my notes. What is simple harmonic motion? Simple harmonic motion is a periodic motion executed by a body where the acceleration is proportional to its displacement from the mean position and will always be directed towards the mean position. So this we call it as what? Simple harmonic motion. Once again, I'll repeat. What do you mean by simple harmonic motion? Simple harmonic motion is a periodic motion executed by a body where the acceleration is proportional to its displacement. Okay, I think someone wants to join. Someone wants to join. Sumit Saurav. Hi, Sumit Saurav. Why so late, man? Okay, Pa, I'll define what is simple harmonic motion. So simple harmonic motion is a periodic motion. What is simple harmonic motion? Simple harmonic motion is, it is a periodic motion executed by a body where the acceleration is proportional to its displacement from the mean position and is always directed towards the mean position, and the force that acts, we call it as what? Restoring force. Once again, I'll repeat. Look here. Simple harmonic motion, you can either define it in terms of acceleration being proportional to displacement or restoring force being proportional to displacement. Okay, so simple harmonic motion can be defined either in terms of acceleration being proportional to displacement or restoring force being proportional to displacement. Okay, so why is this? Because force is equal to mass times acceleration, or acceleration is force by mass. So therefore, by Newton's second law, you can discuss things or describe a system either in terms of how it accelerates or how the force acts. So both acceleration and force are connected with each other. Okay, now look here. What does this mean? Again, I'll give the following example. Okay, look here. I'll go towards paint. So I'll undo all this. Now look here, Pa. I'll consider two cases. Okay, this is again same thing. Okay, I think I'll put it this way. So this is a spring. Okay, I think I can avoid writing this. Look here, I'll consider two cases. One, this is first case. Okay, the first case is, this is equilibrium position, correct? In my diagram, this is the equilibrium position. First case is the body is pulled away from its equilibrium position over a distance of say 5 meters or 5 centimeters. This is 5 centimeters. Okay, this is case 1. I'll consider second case. What is the second case? The second case is, again, this is my equilibrium position. Okay, the body is pulled at a distance of say 20 centimeters. This is 5 centimeters, other one is 20 centimeters. This is 5, this is 20 centimeters. Okay, what is case 1? Case 1 is, what is case 1? Case 1 is where the object is pulled by a small distance which is 5 centimeters. This is case 1. What is case 2? Case 2 is the body is pulled from the equilibrium position O by a large distance which is 20 centimeters. Correct? Now the question is, in which case will there be more restoring force? Okay, we all know, right? Restoring force will act upwards. Can you see here in my blue color line? Restoring force will act upwards. So in which case will there be more restoring force? Is it in the first case or is it in the second case? Where will be the restoring force be more? Large displacement or in small displacement? Hi students, tell me no. People are not
Large
there.
displacement, sir.
People are not there. Show participants. Yeah. Bharat. ET5, are you there, man? So in which
Yes,
case
sir.
will the restoring force be more? Is it in the second case or first case?
Second case.
Second case, precisely. Okay, understood? Look here. If I pull the object, so in which case will the restoring be force? Restoring force will be more in the second case. If I pull it by a large distance, then the restoring force will be more. Okay, clear? Therefore, this is equivalent to telling that restoring force is proportional to displacement. Once again, I'll give the following example. Take a rubber band. Okay, take a rubber band. Keep one end fixed. Keep your left hand fixed. Keep your right hand to pull it. Case 1 is you pull the rubber band by 5 centimeters and leave it. Case 2, you take the same rubber band and you stretch it over 20 centimeters. Okay, big distance, and if you leave, what will happen? The rubber band will come and rebound on your hand with a bang on your hand with a large force. Correct? No? Am I right? If you take the rubber band and if you expand it by a large distance and leave, it will hurt you because it is going to come and bang your hand or rebound your hand with a larger force. Likewise, so if I take this object and if I pull it by a large distance, then you see that restoring force is proportional to displacement. That is what precisely this definition is. Is this clear? Understood? Take a rubber band, stretch it by stretch it by some distance. Larger the distance you stretch, larger will be the restoring force acting on it. Therefore, it will hurt you. Okay. So, therefore, what does that mean? What does that mean is I'll undo all these stuffs. Okay. What does this mean? Simple. Look here. I'll take a red color. You pull this object over a distance x, and the restoring force will act in the upward direction. This is the direction of the displacement. This is the direction of displacement which is downward. The direction of restoring force of the spring after I withdraw my rubber band is upwards. Okay, clear? Therefore, this can be written as what? This can be written as an equation. What is that equation? Look here. I'll simply write F is proportional to x. You see here. I'll simply write restoring force F is proportional to my displacement x. Okay, clear? Is this clear? What do you mean by simple harmonic motion? The case of simple harmonic motion, the restoring force will be proportional to displacement. This is one part. This is one part. Okay, this is one part of the definition. Okay, by the way, what is force? Is it a scalar quantity or is it a vector quantity? Force is a vector quantity, correct? Therefore, it will have both magnitude and direction, correct? Once again, observe here, okay? Once again, observe. I'm pulling the object in the downward direction here. In what direction is the force acting? Restore force acting in the upward direction, correct? If I pull it downwards, restoring force is acting in the upward direction. That is in the direction opposite to the direction of displacement. Therefore, this can be written as what? This can be written as, so F will be equal to minus a constant times K times X. Is this clear? What is the equation of a simple harmonic motion given by? The equation of a simple harmonic motion is given by restoring force is proportional to displacement. I'll use a blue color. Yes. So you see that restoring force is proportional to displacement. Therefore, F can be written as a constant times X. But in what direction does the restoring force act? It acts in a direction opposite to the direction of displacement. Therefore, it is given by minus Kx. Okay, is this clear to you all? How does the restoring force is connected with the direction of displacement? They are acting opposite. So therefore, what is this? This equation I call it as what? F equal to minus kx. It is simply called as Hooke's law. Okay, what is Hooke's law? Hooke's law states that within an elastic limit, stress is proportional to strain. Therefore, you see that within some limits, force is proportional to x, or F is equal to minus kx. Is this clear to you all? Is this clear to all students? सब लोग
Yes,
Yes,
sir.
sir.
Yes, sir.
अब समझ पा रहे हैं ना?
Yes,
सब
sir.
लोग समझ पा रहे हैं ना? ಎಲ್ಲರಿಗೂ ಅರ್ಥವಾಗುತ್ತಿದೆ ಎಲ್ಲವೇ? You're able to understand, right? This much is fine. Okay, so definition of simple harmonic motion is done. Okay, next we'll move. I'll review fast. Okay, all these terms that I have written on my notes is what I have explained. Okay, next, where are we? Yeah, next we will look at, where is my doc file? Yes, now we will see. Okay, look here, examples of simple harmonic motion. There are two examples. One is simple pendulum that makes an angular motion. Next is a body of mass m which is connected to a spring. That is what I am considering throughout. Okay, next, properties of simple harmonic motion. So what are the properties of simple harmonic motion? I will take the example of a simple pendulum. So I will just tell how does velocity vary with time. That's all. Okay, yesterday I think using Usain Bolt 100 meters race, I illustrated that point. So therefore let me just recollect or say the same stuff. Okay, look here, I'll undo all these parts. Okay, look here. What happens? Shall I use my mean position here? Yeah, this is my mean position O. Okay, look here, Pa. I'll just put it in this way. Can you see here in my diagram? O is my mean position. Okay, if the object moves here, what happens? It approaches the mean position, blue line. Here what happens? It moves away from mean position. It is moving away from blue line. Now what is happening? It is approaching the blue line, approaching the mean position. Now again what is happening? Moving away from equilibrium position. Okay, so therefore let me tell the following. How does the velocity vary with time? Look here, if the object approaches the mean position, velocity will increase. At mean position, velocity is maximum. Then can it come to rest? No, because of the tendency to move further, it will go up. When it goes up, when it moves away from equilibrium position, velocity will decrease. Okay, so therefore how does the velocity of the object vary with the time? I'll put in simple words. If it approaches the mean position, velocity will increase. At the mean position, velocity is maximum. So when it moves away from equilibrium position, velocity will again decrease. At this point, which we call it as amplitude, velocity will be zero. Okay, therefore how does velocity of an object vary with the time? If it is performing to and fro motion. Okay, to and fro motion means what? It is up and down motion. Okay, for the spring. So how does the velocity vary with the time? Look here, I'll read out in my notes. Variation of velocity of a body executing simple harmonic motion. How does the velocity vary with the time? Can you see here? The velocity of the body decreases when it moves. Okay, let me put here. The velocity of the body increases when it approaches the equilibrium position. That means what? In my diagram, it is this. Okay, I will use a different color. Okay, if the body approaches equilibrium position, then the velocity will increase. That is this. Next, what happens to the velocity of the body? The velocity of the body decreases when it moves away from equilibrium position. Where does this map into my diagram? So if the body moves away from the equilibrium position, correct? When it moves up, its velocity will decrease. Okay. Next, What is the next point? Next point is the velocity becomes maximum while crossing the equilibrium position. Correct? What does that mean? What does that mean? Okay, so look here, I'll undo all these steps. So if the body, so if the body, look here, if the body approaches upward direction, so in equilibrium position at this point, its velocity is maximum. Okay, so what is the third property? Third property is when the body crosses the mean position, velocity is going to be maximum. Is this clear? Once again, I'll take the example of Usain Bolt's 100 meters running race. Okay, so when the athletes move and when they approach the finishing line, there, when the athletes move, what happens? Their velocity will increase with the time. And near the finishing line, their velocity is going to be maximum. So therefore, likewise, here what happens? When the object approaches the mean position, its velocity is maximum in the mean position. Okay, so can you see here? Once again, let us recollect Usain Bolt's 100 meters running race. Browser. Okay, can you see here? 100 meters running race. Again, look here, all these concepts are interrelated. Okay, and I was also an 100 meters athlete sprint during my high school and PU days. Okay.
Can help. This sentence is grammatically correct. First time I've seen that. Chambers in 1, Burns in 2, Bailey in 3, Bolt, the Olympic champion and world record holder in 4, Gay, the defending champion in 5, Powell, the fast man who usually fails to deliver in 6, Patton in 7, Thompson in lane 8. Away first time, good start from the Bulls. Bolt leading the moment going away. Gay trying to go with him, and he's going big drag through the second place, but he's going to win it by 2 meters. 9.58. The world record's gone. That's not.
Okay, so I think I will explain that concept. So how does velocity vary with the time for an object performing simple harmonic motion? Look here, this is my position of equilibrium. Okay, for a simple harmonic motion in the 100 meters running race, I call this as finishing line. Okay, so if Usain Bolt approaches the finishing line, what happens? His velocity will increase, and near the finishing line, I'll use a different color. So when he approaches the finishing line, what happens? His velocity will increase, and near the finishing line, his velocity will be maximum. Okay, then after crossing the finishing line, what the athletes do? They will slow down. Correct? They will slow down. So therefore, velocity will decrease. Okay, here no. So if an object approaches the equilibrium position, velocity will increase. When it crosses the equilibrium position, velocity is maximum. When it moves away from equilibrium position, the velocity is decreases. Okay, this is the characteristics of a body executing simple harmonic motion. Okay, what does that mean? How velocity varies with time. So everything is captured in my 4 points here. Okay, so how does velocity vary with the time? Everything is being captured in my 4 points here. Velocity decreases when it moves away from equilibrium. Velocity will increase when the body approaches the mean position. It is maximum at the mean position, and it will be 0 near the amplitude. Okay, this part is done. So time is 10:15. I think I have 5 more minutes. It's done. Okay, anyone having any doubts? Anyone having any doubts? Okay, definition of simple harmonic motion. I've already told. What do you mean by simple harmonic motion? So it is a to and fro motion in which the acceleration or restoring force is proportional to displacement. F is equal to minus kx. That's all. Okay, which is Hooke's law. Then this part also we discussed. How does velocity vary with the time? Already discussed. Usain Bolt will approach the finishing line. He will move away from finishing line. Body will approach equilibrium position. It moves away from equilibrium position. That is done. How does the position of the object vary with the time? I already told. All this could be explained with the help of a sinusoidal signal. Therefore, it can be given by x of t is equal to a into sine of omega t. Okay. How does the velocity of the body can be described? Velocity of the body can be described by x of t equal to a into sine of omega t. Okay, can you see here? All sinusoidal signal, all simple harmonic motion can be described by a sinusoidal signal which is given by x of t is equal to a into sine of omega t. That's also done. Okay, next, what is the last part? This is done. And what are the three different cases of motion we have? The three different cases of motion we have is, we will discuss the theory of free oscillations, then damped oscillations and forced oscillations. Okay, then there is one more thing, the differential equation for a simple harmonic motion. So what is the differential equation for a simple harmonic motion? So can you see here? Look here. Can all of you see here? Suppose I write the object by x of t. All of you can see here what I have written. I have written a sinusoidal signal. Okay. Suppose a body is described by x of t is equal to a into sine of omega t. All of you know my earlier example where I have shown the paper. If you take a paper, you see here, browser, okay, sign bold. You've seen this video that I have already done. Okay, what is that?
आपको पता है, I'm not classically trained, but I didn't let that.
Okay, can you see here? If an object performs to and fro motion, okay, that can be completely described by a sine wave. Okay, that is what I have written. X of t is equal to a into sine of omega t here in my doc file. Okay, so where is that? Below. Okay, this is what I have written. X of t is equal to a into sine of omega t. What is x? I think I'll use a bigger font size, for example, 12, 15. Okay, is it visible? What is x? X in my diagram is nothing but this distance, x. Okay. Now, what is velocity of the body given by? Velocity is dx by dt, correct? If you differentiate equation 1, what you are going to get? Velocity as a function of time. Velocity as a function of time. This will be equal to a into what is d by dt of sine theta? Cos theta, correct? So it's going to be cos of omega t. And what is d by dt of omega t? omega. Correct? No? So you will have omega coming out. So therefore, what is the velocity of the body given by? Velocity of the body is given by, velocity will be equal to A omega into cos of omega t. All of you are able to see? Okay, I'll call this as equation 2. So what is x? From equation 1, it is the position of the object. And what is velocity from equation 2? It is dx by dt, which is this. Now what is acceleration? Acceleration is d square x by d of t square or dv by dt. Correct? Let us find acceleration. What is acceleration? Acceleration will be equal to dv by dt. Therefore, differentiate equation 2 with respect to t. If I differentiate equation 2 with respect to t, what I'll get? This will be equal to, I have a omega. What is d by dt of d by d theta of cos theta minus sin theta, correct? So this will be equal to minus sine of omega t. Okay, and what is d by dt of omega? It is d by dt of omega t is what? Omega. Therefore, what I'll get? What we will get is, we'll get omega coming outside. Okay, can you therefore see here? I have minus here. So what is a omega into omega? A omega square. What is a omega square into minus 1? It is minus a omega square. So therefore, what is the equation of, what is the equation for acceleration given by, for a particle performing simple harmonic motion? Acceleration is given by ACCL. Acceleration is equal to minus a omega square, right, omega to the power of 2 into sine of omega t. What is a into sine of omega t from 1? A into sine of omega t from 1 is x of t, correct? No. Therefore, acceleration of the particle can be written as what? Acceleration of the particle that is performing simple harmonic motion, that will be equal to minus a omega square times x. Okay, there is a square here. Okay, acceleration is equal to minus a omega square x. Can you see in my notes here? It's my cursor. So what is the equation for a simple harmonic motion given by? Acceleration is equal to minus omega square x. Acceleration, can you see here? Acceleration is equal to minus omega square times x. Okay, minus omega square, a will not come. Okay, minus omega square times x. So what is the equation of motion for a simple harmonic motion given by? If I start with a sinusoidal signal, its acceleration is given by, can you see here? Its acceleration is given by d square x by d of t square is equal to minus omega square x, or acceleration plus omega square x equal to 0. That is what I have just derived it here. Okay. So I think I'll stop here for today. The next class we will look at the theory of free oscillations and damped harmonic oscillations. So therefore, what are the things we did today? By considering a body which is attached to a spring. You see in my figure here, by considering this example, a particle attached to a particle of mass m attached to a spring, we discussed the following definitions. Which are those? I defined what is displacement, I defined what is amplitude, we defined what is frequency, time period, equilibrium position. Equilibrium position, I clearly described it in terms of considering a finishing line, in an 100 meters running race. Then characteristics of simple harmonic motion, Hooke's law, F equal to minus kx, that we discussed. Then I also told all simple harmonic motion can be completely described by sinusoidal signal, x of t equal to a into sine of omega t. And then we derived this equation for simple harmonic motion, that is d square x by d of t square is equal to minus omega square x, or acceleration plus omega square x equal to 0. Okay. So I'll stop here. Does anyone have any doubts? Does anyone have any doubts? And the notes also have shared it in the WhatsApp group.